Good morning, everyone. Thank you for joining us today. So in our last series, we journeyed across the entire computing continuum, right? From the massive power of the cloud all the way to the intelligence at the edge. Well, today, we are kicking off a brand new journey into the automated world. We're living in this incredible age where technology isn't just a tool we pick up and use anymore. It's an active player. It's this network of non-human actors doing things all around us, from the heavy lifting on a factory floor to the invisible logic that decides what you see online. Okay, let's dive right into this and build ourselves a really clear technical framework to understand the forces that are, quite literally, reshaping our world.
This quote really hits the nail on the head, and it's the perfect place for us to start. Automation has become this pervasive, almost invisible force. It's woven so deeply into the fabric of modern life, but most of it is hidden from view, you know? It's humming away behind server racks and inside factory walls. So our goal in this series is to pull back that curtain. We're going to give that ghost a name, a history. We'll learn its language, trace its evolution, and really analyze its impact from a solid engineering and computer science perspective.
And that right there brings us to the absolute core of what we're doing today. In everyday chat, people throw around robotics and automation like they're the same thing. But for us, for anyone in tech, engineering, software, that distinction is absolutely crucial. I mean, mixing these terms up can lead to some seriously flawed project scopes, totally misunderstood capabilities, and honestly, some bad investment decisions. A precise vocabulary is the foundation of good engineering. So today we're going to build a rock-solid framework so we know exactly what we're talking about.
To build that framework, we're going to climb what I like to think of as an evolutionary ladder of concepts. We're going to start at the very bottom, with the most fundamental ideas, and work our way up, rung by rung, to the super complex, intelligent systems we see today. Each step on this ladder, it represents a massive leap in what's possible, a new layer of abstraction, and a greater and greater degree of autonomy that we've handed over from human to machine. This isn't just a timeline, it's a conceptual stack, where every new layer is built right on top of the one before it. Let's start at the very bottom.
Okay, let's get our footing on that bottom rung. Before we can even start talking about automation or robots, there's a concept that's even more fundamental, one that really changed the entire course of human history and productivity. It's the base layer, the foundation. What is that single core idea that started this whole thing?
And the answer is mechanization. This is the bedrock. Its main goal is just elegantly simple: to replace or multiply muscle power, to get past the physical limits of our own bodies. Just think of a simple conveyor belt. It can move heavy stuff all day long with tireless strength, but it still needs a person to flip the switch, set the speed, and decide what to do with whatever's on the belt. The machine is handling the doing, but the control, the decisions, the thinking, that's all still in human hands. And this applies to everything from a simple water wheel to a printing press to a car engine.
For a long time, mechanized systems were basically single-purpose machines. You know, a power loom could weave cloth way faster than any person. But if you wanted to change the pattern, that was a huge manual process of basically re-engineering the machine itself. But then, in 1804, an invention came along that planted the seed for everything that came next, from the first robots to the supercomputer in your pocket right now.
The key innovation here was programmability. The Jacquard loom used this chain of cards with holes punched in them, and the pattern of those holes literally told the machine which threads to lift to create the design. The absolute genius of this was separating the machine's hardware from the task's logic. To weave a totally new design, you didn't have to rebuild the loom, you just fed it a new set of cards. This was the first time a stored program was used to control a machine. It's a direct ancestor of Charles Babbage's analytical engine and, of course, the punched card systems that were the backbone of computing for decades.
So, mechanization gives us programmable muscle. Awesome. But even the Jacquard loom was still, for lack of a better word, dumb. It had no clue about its own state or the quality of what it was making. If a thread snapped, the loom would just keep on chugging, mindlessly making flawed fabric until a person noticed and stopped it. This big limitation, this lack of self-awareness, is what created the need for the next giant leap up our ladder: automation.
The critical shift here is moving from just augmenting muscle to actually delegating control. And this slide shows that difference perfectly. Mechanization is what we call an open-loop system. A person gives a command, the machine does it. End of story. Automation, on the other hand, introduces a closed loop or a feedback system. The system can actually measure what it's doing, compare that measurement to a goal or a set point, and then change its own behavior to fix any errors. The classic example is the thermostat in your house. It senses the room temperature, compares it to the temperature you set, and then turns the furnace on or off to maintain it. That self-regulating feedback loop, That is the very soul of automation.
All right, now that we've nailed down the core idea of automation, delegated control through feedback, let's see how it actually shows up in the real world. Specifically, in the place where it first had a massive impact, the factory floor. So how does this concept play out in a big industrial setting?
Generally speaking, we see two main types. The first is fixed, or hard automation. This is your classic car assembly line where every single station is a custom-built machine designed to do one thing, like welding one specific joint over and over again, millions of times. It's incredibly fast, super efficient for mass production, but it is completely inflexible. Changing it for a new car model is a gigantic undertaking. The second type, programmable automation, is where the spirit of the Jacquard loom really comes to life. Here, the equipment, like a modern CNC machine, that's computer numerical control, can be reconfigured super fast just by loading a new software program. The exact same hardware can be used to mill engine blocks one day and then custom aerospace parts the next.
Okay, let's take this concept out of the factory and into our everyday lives. The ATM. It's probably one of the most successful and widespread examples of automation that we all interact with. It took this complex, human-driven process, withdrawing money from a bank, and just completely automated it. So how exactly does it fit our definition of an automated system?
The way an ATM works is a perfect case study in delegated control. You give it your input, sure, but then this complex control logic totally takes over. It creates a secure network connection to the bank servers to check your identity and your balance. Then it uses these precise mechanical parts to count and give you the cash. And, crucially, look at step 4, it has internal feedback loops. Little optical sensors confirm that every single bill was dispensed correctly. If a bill gets jammed, the system knows. It logs an error, and it goes into a safe mode. It's a masterpiece of automation. But, and this is a really critical point we're about to get into, it is not a robot.
And this brings us to the next big rung on our ladder. We've just firmly established that an ATM is a very sophisticated automated machine, but it's not a robot. So, what's missing? What is that defining feature that takes an automated machine and elevates it into the category of a true robot?
The defining characteristic is this triad right here: sense, process, act. A robot is the physical embodiment of automation, but it's specifically designed to perceive and interact with the messy, unpredictable, physical world. An ATM's entire world is internal and perfectly controlled. A robot's world is external and chaotic. It has sensors, like cameras for vision, or LiDAR, which uses lasers for light detection and ranging to build 3D maps to see its surroundings. It has processors, its onboard brain to make decisions, and it has actuators, motors, grippers, wheels to physically do things in the world. It is the bridge between the digital control and our physical reality.
So now, we've climbed from muscle to control to a physical body that can sense and act. We have a robot. But for decades, that robot's brain was still just following a very rigid set of pre-programmed instructions. The final and honestly the most transformative layer on our ladder, artificial intelligence, changes that entire paradigm.
I absolutely love this phrasing. If robotics gives automation a body, AI gives it a mind. The principle here is the delegation of judgment. Traditional automation follows these strict if-then rules that a human programmer writes out. An AI-powered system, usually through machine learning, isn't just given rules. It's trained on huge amounts of data to develop its own rules. It learns to see patterns, to make predictions, and to adapt its behavior to new situations that its creators never even thought of. It can handle ambiguity, and that, right there, is the essence of judgment. Okay, we've now defined all 4 concepts on our ladder. But out in the real world, the most powerful and advanced systems aren't just one or the other. They are this synergistic stack of all 4, with each layer making the next one possible. So how do they all combine to create the intelligent machines of today?
This summary table lays out our whole journey perfectly. Let's use it to break down an advanced warehouse robot. The motors in its wheels and its lift, that's mechanization. Its ability to follow a preset path using feedback from wheel sensors to correct its course, that's automation. Its physical form, with LiDAR to sense the environment and a gripper to pick things up, makes it a robot. And its ability to use a camera to identify a product it's never seen before, or to dynamically figure out a new route around an unexpected obstacle, that is artificial intelligence, the delegation of judgment. You see, every single layer is essential for the whole system to work.
All right, so we've got the concepts locked down. But where did the modern robot actually come from? I mean, the dream of an artificial helper is ancient. It shows up in myths all over the world. But the reality, the actual engineering history of the industrial robot, has a very specific birthday. The intellectual journey to the robot is a long one. We've already seen how the Jacquard loom played a part. A really pivotal moment came in the 20th century with the development of control theory and cybernetics. The science of control and communication in animals and machines, pioneered by people like Norbert Wiener. That work gave us the mathematical language to build self-regulating systems, and all of this theoretical groundwork was building towards one key, practical moment.
1961. This is the year. A 4,000-pound robotic arm called Unimate 001, invented by George Devil and commercialized by Joseph Engelberger, started its very first shift at a General Motors plant in New Jersey. And its job was brutal. It was picking up red-hot metal parts from a die-casting machine and dunking them into a cooling bath. The air was filled with toxic fumes, and the risk of getting hurt was incredibly high. The Unimate did this dangerous, mind-numbing task 24/7 without a single complaint or getting tired. Its success was a monumental moment. It proved that robots weren't science fiction anymore. They were practical, reliable industrial tools that could completely change manufacturing. The robotics revolution had officially begun.
From that one single massive arm in 1961, an entire automated ecosystem has just exploded, and now it underpins pretty much every single sector of the modern economy. So let's fast forward from that moment to right now. Where is this automated ecosystem making its biggest impact today?
We can really break down modern automation into three key areas. First, you've got the physical world of manufacturing and logistics, where actual atoms are being moved and put together. Second, there's the invisible digital world of software and business processes, where it's all about manipulating bits. And third, there's the public-facing world of systems that we interact with every single day. Let's look at an example from each one.
In the physical world, automation has totally revolutionized logistics. Huge e-commerce warehouses run on fleets of thousands of autonomous mobile robots, or AMRs. Now, unlike the older automated vehicles that had to follow magnetic stripes on the floor, these AMRs use onboard sensors and AI to navigate dynamically. They run on a goods-to-person model, where instead of a person walking for miles up and down aisles, the robots lift and carry entire shelving units directly to a stationary worker. This is the core tech that makes the insane speed and efficiency of next-day delivery even possible on a global scale.
Now let's talk about the invisible world of software. Robotic Process Automation, or RPA, doesn't use physical robots at all. It uses software bots to copy human actions on a computer to automate repetitive digital work. This slide shows a classic example, processing an invoice. An RPA bot can be trained to do this whole workflow, logging into an email, opening an attachment, using character recognition to pull out the data, entering that data into an accounting system, and then archiving the file, exactly like a person would, but at lightning speed, 24/7 with zero copy-paste errors. It's a huge deal in back-office operations.
And finally, we have the automation that touches our lives most often, usually without us even noticing. Our entire digital life is curated by these massive, complex automation systems. As this chart shows, a huge piece of this is recommendation engines. The algorithms on streaming sites and online stores that predict what you might want to watch or buy next. But just as important are the spam filters cleaning our inboxes, the real-time fraud detection systems checking credit card transactions for anything weird, and the incredibly complex ranking algorithms that decide the search results and social media feeds you see every single day. These are all automation systems working at a planetary scale.
Wow, we have covered a ton of ground, from the mechanics of the 1800s all the way to the algorithms of today. So let's bring it all together. What is the single most important idea that you should walk away with from this foundational explainer?
This, right here, is the key takeaway. Automation is not a single technology. It is a long, evolving quest to delegate human capabilities to machines. We've seen that clear hierarchy. Mechanization gave us machine muscle. Automation added control logic. Robotics gave that logic a physical body to interact with the world. And now AI is giving it a mind that's capable of judgment. The physical robots in a warehouse and the invisible RPA bots in an accounting firm, they aren't separate things. They are two sides of the very same coin, and they're driven by the exact same fundamental principles.
So now that we've built this foundational vocabulary, we have the tools we need to go even deeper. And in our next explainer, we're going to do just that. We're diving into the anatomy of a robot. We'll be moving from the conceptual to the concrete, exploring the incredible technologies behind how robots sense the world, how they think about what to do, and how they ultimately act on their environment.
Thank you all so much for joining us for this deep dive. I really hope this has given you a clear, structured way to think about the automated world. To continue this journey with us and explore all the fascinating intersections of technology, AI, and beyond, please be sure to subscribe to our channel tech, AI, and beyond. We'll leave you with this final thought to chew on until next time. We are building ever more capable artificial partners. The ultimate question isn't what they can do, but what we will choose to ask of them.